Hey, short recording about the homework assignment on CAMS, and I'm going to do for you the case where both the lift and the fall are linear, simpler equations to program, and then I'm taking the rise being 100 degrees, and then the upper dwell from 100 to 160, that is 60 degrees, and then the return will be 80 degrees. So at the end of the upper dwell, 160 plus 80, 240, and the rest to 360 is going to be the lower dwell. This is follower displacement. It includes a bias, which is function of the base circle radius. They go hand in hand. You either impose a basic radius or the original bias. In the programs that I'm providing you with, there's the bias that you set up. So what is with star is a no bias displacement. So it starts at 0, ends the lower dwell, it's all 0. So let's it says here go in 1 degree increments. So I'm going to populate the first column 0, 1, 2, 3, 4, and drag it down all the way to 360. Come on, 360 too much. So come on. $45, $55, okay, 60. And then the second column is for theta star. This is the current or cam angle that starts at the beginning of the rise. Theta star and theta are the same. At return though, theta start, it's going to be theta minus 160. Okay, so you can either do a change of variable, that will be easy. So for the return for the fall, we're going to just say theta minus 160, or you can define a second column that is, you're not going to use it only for the return. Okay, so let's take care of the the dwells first. So I have the upper dwell for the translating follower. It's 0.012. So it begins at 160. I go 160, and so 160. Let me take that back. I know so yeah, I could do it, but then I need to go back, or let's just leave one cell blank, because it's not going to extend. So this was 160, 161. I said 0.0012, and no, copy, and then go paste, and at 240 I got myself confused. Okay, so no, it's the upper dwell, it starts at 100 and ends at 160. Okay, so let's go back to where we were. Delete this, and so this will be the last one. 0.012, 12 millimeters, and then copy, and then paste, going all the way to 101. So paste. Okay, so this would be the upper dwell, and then the lower dwell, it starts at 240 and goes all the way to 360. So 240. Let's go 241, and that's 0, and then goes all the way to 0, or to end of the 360. Paste. Okay, so I have the lower dwell, I have the upper dwell, and then I need to fill in the rise. For the rise or lift, I have S star is using theta star, but theta star and theta are the same, so I'm going to say equals L. Let me define an L. So L, let's call it, alright, so I say L equals, and L equals, we said 0.012, and this will be an input value. See if the L is at, yeah, it was accepted, and could have used L earlier. Anyway, so I have equals L times would be theta, okay, and then divided by the way it started. Beta is it's hard-coded, so beta is just going to be the 100 over 100. Okay, so I say copy and then paste all the way to where the upper dwell begins. Paste, and of course it should end with 0.12. Let me change the color of the, could be of the font, or could be of the highlight, the background. All right, so we have the upper dwell, the upper dwell and the rise, the lift, and now I'm going to do the return. And for the return, I could just say, use this column, and doesn't make sense to go past the, so yeah, I 1, 2, 3, 4, 5, 6, 7, and only now I expand it, so 7, and this is going to be the theta star for the return phase. And for the return phase, the equation is, we're looking here, so it's going to be L1 negative theta star minus beta. Okay, so beginning with so for the return I have equals L times, I said 1 minus this value over and the duration of the return is 80. Okay, so we went to 0 indeed. So is the equation, it makes sense. It stopped at 0. So we do have now the values generated, and we can plot the graph of one versus the other one. A lot of scrolling. So let's see if I take this one, 360, and then this one, and do a plot. Should be, let's see, it goes insert charts, and I'm doing this. Okay, so I have for linear functions, linear motion programs. I have the graph, and it appears correct. If I want instead I'm just changing L to 20, and I'll get the graph for the oscillating follower. So what I could do is to just take, this is where having them back to or side to side, side by side, it's a little bit better. So it appeared to be convenient to have the in-between column of theta star, but using the change of variable would have been probably better. So I have copy, and I say paste values, paste special, and it's the values. Okay, and then I have 0, 1, 2, 3, 4. Okay, I'm redoing the first column. All right. So it's copy. No, rather the both columns. Copy. .360 all the way to 360. So it's copy, and then add it and paste. So I have a text. This is for Octave. If you're using instead MATLAB, then no need to go through these steps of saving it to an ASCII file. So file, save as, and I'm going to where my MATLABs are. MATLAB and CAMs. So this CAM translating motion. So this CAM. So let's see, CAM 1. Alright, and I'm going to Octave now, and this is for translating follower, and the name of the input file is CAM1. Okay, and see what it does. Change directory. So it should repeat the graph, and it did. And then looks like MATLAB is more forgiving here. So okay, so we've got actually so this is translating face follower the way I left it last time. Actually, it was a recording of it. And so let's look at the description here. You need to go in parallel with the paper, and you've got it from me. So CAMs, MATLAB. Is this MATLAB? No, CAMs, and we have. All right. So we have the paper, and let's look at the figures. So for translating follower now, and so the angle, it should be 0, roller radius should be 0, eccentricity should be 0. And okay, so I'm going and change all these. So follower bias, something that you choose. It appeared big earlier. So big Y, because I have the amplitude of follow motion was 0.01 and the bias was 0.8. That's a lot of bias. Follower eccentricity, we said, is going to be 0. Face length, probably, I mean, it should be comparable with the bias, 0.5. Again, it's something that you will have to figure out. It's not like I'm going to advise you on these proportions. Roller radius, it's 0, alpha at 0. So let's try again. And it always takes longer. Okay, well, it's dented here. Looks like the what we have, the bias is too small. I need to increase the bias, and also I need to increase the limits of the second plot. Okay, so increase the bias as 0. Let's make it to 5. So 5. And then for the second plot, we have the figure 2 axis, RB bias. Let's see how it looks. I may have to increase this value here. Okay. Like I said, it takes forever. Okay, so we have something. Cam is apparent here. If I want to see the full envelopes, I would need to increase the limits here. So if you look at axis, goes from -2 base circle radii. 0.8 is the eccentricity. 0.8 eccentricity. So, but it's 0, so it doesn't help. So we can make this equal 3, and now we'll see the full envelope. Yeah, let's wait for. Okay, so I'm back. So we have the follower, 0 eccentricity. Maybe a practical cam should have a little bit bigger bias, that is bigger base circle radius. You take make a copy of this. You clear figure, reset figure file, save as. Either take a screenshot or do whatever. So Alt print screen, and you go to paint. Well, I should maybe save this. Okay, so yours. All right, and this is it. As for don't save, there is one more part to the Excel spreadsheet to do velocity and acceleration. To get ds and ds star are the same, ds over dt. All right, so ds over dt. So ds over dt, this is going to be equal to ds. Maybe I should. So I have what? Precise. I have ds over dt. This is equal to ds over d theta times d theta over d t, and I have this piece here is going to be omega. okay? And in order to, and I need to work with the angles in radians. So let's sacrifice this, or rather, move this to the side. I'm done with this. I need to delete it. No, let's keep it. So I'm moving this, and I have the angle in radians. Copy and paste. And then I have here equals this value times pi over 180. So I have the angle radians, and I need an omega. So it would be omega is 300 times pi over 30. Okay, so this is radians. Okay, and this is omega. Alright, so I have omega, and we said this is going to be equal to alright, so we have the center difference. I'm going to do center difference, and at the end will be forward and backwards difference. So it's going to be next value minus future value, the increase over the increase in theta. No. Let me move this because I want to have them in order. So this is just going to be here. Okay, so back again, beginning with the second value, I have equals ds, next value minus previous value, so center difference divided by the change in theta. Okay, and then times omega. Okay, and so I have the last one is not going to be a the last one is not going to be correct because it refers to value that don't exist. So I'm doing this is backwards difference, and the first value, if I do the same, I copy this and then paste, I have to, so this will be forward difference. The rest is center difference, and I can look at the plot of the graph, and this is the velocity graph. Now what you're going to do, I need to go to a WebEx meeting, so you need to repeat this now and do so copy and paste, and you need to do the d2 over dt squared, even you can superscript, and repeat what I did working with the ds over dt column and of course theta column. I could just copy this and then paste. Of course it's going to index, so I need to move it back, or just follow the same steps. Okay, and expand it all the way down with the fixes at the beginning of the end. And you can see here, if we have finer step for theta, you see bigger spikes. So we have infinite acceleration. You can even look at it in terms of degrees to recognize where the, so I have beginning of the upper dwell, infinite acceleration, end of the upper dwell, beginning of the fall, infinite acceleration, end of the return, infinite acceleration. And actually, if I do copy and paste, and then if I move them, we'll see also there's a spike at the beginning of the rise, or it should be a spike at the beginning of the rise. Well, it's missing. Anyway, so this was it. The graphs will of course look different for your case, and good luck with the homework.